Okay, so you cannot minimize Zoom while you're recording this meeting. What?
Oh, I see you, Professor. Seems good.
Great. Okay. All right. Share my screen again. There we go. All right. So we see here that this is just our code word. We have the systematic code word. We have D plus the parity bit portion of the code word. And now we're going to define this H transpose, just denoted T. Okay, so we're going to start with the transpose, and that is going to be this P and IM, and we're going to call that our parity check matrix. Now, by this relationship up here, this C times this guy, where C is this, that should equal 0, right? And that's how we're going to check our received code words. So if we looked at H, then we would just end up in this relationship here. So okay, now consider a received word R. Okay, that's what we're going to receive, and the receiver is going to do its digital demodulation, use all the stuff we learned before spring break to try to estimate each of those bits out of that set of symbols, right? So we're going to collect up some number of bits, that estimated bits from the receiver that correspond to the code length, right? However long that code word is. In this case, the one we're looking at, the Hamming 7,4,3, that N is equal to 7. So we're going to gather up 7 bits, and we're going to try to figure out if those are legitimate, and if they are, what message corresponded to those. So if we assume that we have some errors, we're going to call those errors, we're going to describe those using an error vector, where anytime there's a 1 in a bit position of E, it's going to indicate that that bit was flipped. Okay, so that was an error. If it's a 0, there was no error, but a 1 in this vector E is going to indicate that there was an error, right? Because when we do this modulo 2 addition to the sent code word C, then if it's a 0, it doesn't change that bit in C. But if it's a 1, it's going to change a 0 to a 1. And also by the modulo 2 addition, it's going to change a 1 to a 0. 1 plus 1 is equal to 0, right? So we're going to say that our R is composed of the originally sent or transmitted code word, modulo 2 added with this error vector. Now, if we know this error vector, then we know a lot, right? So that's what we'd like to try to figure out. So, for example, if our message is D 1100, then our code word sent would be 1100,011. Okay, according to this Hamming 7,4,3 code. the error vector, let's assume, is 0, 0, 1, followed by a bunch of zeros. So if we modulo 2 that with this C, then we'll have the first 2 digits are unchanged, but the third one is changed from a 0 to a 1. And then the next set of digits are the same. So we look at this R and we can kind of predict that that's not going to be a legitimate code word. Okay, so now we're going to define this S, and we're going to call this a syndrome. And we're going to take this R and multiply it by this H transpose and see what we get, right? So if you look at here, if we take our true code word and multiply it by this H transpose, HT, we should end up with 0, right? So, but now we've got this R and we multiply it by the HT. In this case, we're going to end up with 0, 1, 1. Okay, and oops. So now we have this little bit of information. What can we do with it? All right. So, well, what we really want to do is come up with that error vector. If we know which bits are flipped, we can reverse that process, right? And come back with the true code word. So the problem is S is not unique, since R can be produced by other combinations of C and E, right? So if you look at this, R is 1, 1, 1, 0, 0, 1, 1. Okay, well, let's go back to that table. 1, 1, 1, 0. What is it? 1, 1, 1, 0, 0, 1, 1. Okay, so that kind of looks like this one, right? Which we know that's the one we started off with. But you could probably derive that from some of these others, right? It might take more bits to actually cause that error. But you could end up with that from some of these other code words, just with different bits or more bits being changed in that error process. So so S is not unique. We can't absolutely go from detected S, okay, to the error vector, to the code word, to the message, data message actually being sent, absolutely or unambiguously. But we can take advantage of our maximum likelihood type things. Remember, we looked at for receivers where we're mapping symbols to bits. We talked about a maximum a posteriori probability receiver, a map, and then we said that when the symbols are equal probable, we can use the maximum likelihood receiver. So we're going to do a similar thing here. We're going to adopt this BCS model, binary symmetric channel. So the likelihood or the probability of changing a 0 to a 1 is the same as the probability of changing a 1 to a 0. Again, hopefully that probability is small, but they're going to be about the same, or mathematically they'll be exactly the same, right? So and so what we want is to find choose the code word that is associated with our received R, that where its probability is greater than all the other code word to receive code word probabilities, right? So what's the likelihood that we receive R given that CI was sent, versus what's the probability of receiving R given that any of those other code words were sent. So what we want to do is we want to choose the C sub I that has the greatest probability or maximum likelihood, right? So we can look at this, and not going to dive into this a whole lot. But if D is a Hamming distance between R and CI, then we can come up with this relationship here. And with a little bit of algebra, the key part is that here, this is the D, the Hamming distance. So we want to figure this out relative to this Hamming distance, and we'll note that if well, P sub E is a digit error probability of a binary symmetric channel. So the probability of changing any given digit, right? Again, hopefully that's small, certainly less than 0.5, right? If the probability of an error changing is greater than a half, you've got a really bad channel, right? It's going to be useless. So, but if it's below 0.5, then this ratio here that shows up to the power of D over here, that is going to be less than 1, right? If this is less than a half, this is 1 minus a half, that's going to be bigger. And so the denominator is bigger than the numerator, so it's going to be less than 1, right? So then that means that this probability here on this left-hand side is going to be a monotonically decreasing function of D, right? So if you exponentiate a number less than 1 to greater and greater powers, it gets smaller and smaller, right? If you take 0.9 and square it, you'll get, some value, and you take 0.9 and cube it, that value is smaller, right? It gets smaller and smaller, so monotonically. So what's the result of that? So if we want to maximize the likelihood, then we want to minimize the distance D. Okay. Now, what is that again? That's the Hamming distance between the received vector and the desired code word, right? So we're going to choose CI based upon what is the minimum distance, what's the fewest number of bits I have to flip to make it match R. Okay, so it's basically it's the closest one, the one that looks the closest bit by bit. Okay, each bit is independent. So we want to minimize that distance D. This corresponds to a minimum weight error vector. So an error vector with the fewest number of ones, the smallest error, right? Overall, if you count up the number of bits that are changing. So the fewest 1 bits, fewest error bits, right? So then if we choose that, then that's a maximum likelihood condition. We modulo to that with our received vector, and we will end up with the appropriate code word. Okay, so you can work that out. So we do it on time. All right. So to correct the received code word into the sent code word, we modulo to add the minimum error vector to the received code word. Okay, so now we typically generate a table of this E sub min for each syndrome. Remember, the syndromes are not unique with respect to the error vectors that could produce it, but we're going to find these minimum errors, and we're going to build a table of those, and we'll store that in a lookup table in a receiver, and we'll calculate these things on the fly as we do it. So I've created a homework exercise that'll help you walk through this. But let's go through this example. So a lot of this is from Lothy and Ding, which is, I think, the second reference in your syllabus. Not sure how many of you have located that book and taken advantage of that, but I've replicated some of the stuff here also. Now, let me also point out that a lot of this has also I found a open courseware lecture series from MIT, and I provided a link to that, and I think that's a pretty good reference for you also. So if you click through that, you'll get to some of these type of lectures. And I tried to kind of combine the notation that I used in this lecture between what this MIT lecturer is doing with the Lothy book, and I tended to favor the Lothy because it just works out better. But for example, that this Hamming 743 code is from his lecture. It's a very popular code. That's why he's used it. But so encourage you to follow those, follow that link and look at some of those. But this example is from the series of examples in the Lothy book. So here we come up with a generator matrix. This is not the Hamming 743 matrix or generator code, but it's another one that they've come up with. Here we have 3 message bits and 3 parity bits, right? So here our IK is a 3 by 3, and our parity check, our parity matrix portion of the matrix is these 3 columns over on the right hand side, right? And then we can rearrange those to derive our H of T, right? So we're going to take this P and put it on top, and then the I sub K and put it on the bottom. So we'll have this P on top up here, and then this bottom is the identity matrix, right? So now again, we assume that it's a binary symmetric channel, and we'll use the maximum likelihood decision process and say that our received code word is 100011. Okay, and so now let's calculate the syndrome associated with that. So we're going to take R times H of T. Okay, so that's this. So this is our received R, this is our H of T, and if you do this matrix multiplication, you'll end up with 1100. Okay, and sorry, I can zoom this out again. Now we know that we want to find this E min, so we can modulo 2 add that to R and produce our desired code word, right? So we'll look up in this table. So here's a table of the code. So if you put each of these data words into that generator matrix, you will end up with this set of code words out. Okay, and they have found the minimum error vector associated with each of these syndromes. Okay, and so yes.
No, a sneeze.
I'm sorry.
A sneeze, Professor. Please.
Oh, okay. Sorry. So if you have receive a syndrome 000, there's no errors, right? So happy days right there, right? So our job is done. But if we receive a syndrome of 101, that's going to correspond to this error vector, right? And you see most of these error vectors only have one error in it. That's our minimum, right? Our minimum, the minimum error, well, besides a 0 is going to be where you have one digit. So 1 digit worth of error. So each of these then is going to correspond to a syndrome. Then we'll actually have one left over. And this is the case where you have more than one error in the received code word. So you've had 2-bit errors, and so you might end up this is again is an overdetermined type problem. So you can just pick one. Various different criteria to pick that. But all right, so let's go back to our example. We have this syndrome 110. What does that correspond to? I hope this is right. 110. So that's going to be 001 000 001 000. Okay, so we just looked up that table, pulled it out, type thing. So now we are going to modulo 2 this E plus this received vector R. Okay, so 0 plus 1 is 1, 0 plus 0 is 0, 1 plus 0 is 1, 0 plus 0 is 0, 0 plus 1 is 1, and 0 plus 1 is 1. So this was, in maximum likelihood terms, the code word that was sent. So what's our data message? Well, it's a systematic code. So we look at those first 3 bits in this case, right? This is a 6,3 code. There's 3, K is equal to 3 and N is equal to 6. So there's 3 parity bits and 3 message bits. So we just pick off those first 3, and that's our message. So we see that if we hadn't done this error control coding, we would have thought that the message sent was 100, right? But instead, we now know in reality it was 101. Okay, so that's that example. Your homework is going to kind of replicate some of this with the 743 Hamming code. Okay, and here I'm writing out the parity equations for this particular code. These aren't necessarily magical, but someone Hamming figured out, hey, this is an effective code using these parity checks. You want these to be unique, but yeah. So I'm going to ask, what is the code rate of this code? So how many bits are in the input data message? How many bits are in each code word? This hopefully should be pretty easy to you when you go back and look at this. Write the generator matrix. Now, I gave you the generator matrix in a slide deck, right? So, but figure it out and make sure you understand how you go from these equations to this this matrix here, right? Remember, this first part is the identity matrix, a size K by K, and this is representing your parity equations, right? So in a columnar format, D1 plus D2 plus D4, right? So and D1 plus D2 plus D4. So go through these. And so each one of these are going to represent a column. The one column is going to be ones for each of these D's here, right? And then write out the parity check matrix, write out the code words for each data message in a table, write out the emin corresponding to each syndrome in a table. Now that's might require a little bit of thought. Okay, I didn't describe completely on how to achieve this, except that each of these you're going to have a whole set that are just going to be 1 bits, right? So that might be the little bit trickier part of the assignment here. So then what is the code word that corresponds to the input message 1011? What is the weight of this code word? What is, so you're just going to take this and multiply it by the generator matrix, right? This is your D multiplied by G. That should give you the code word. The weight is the number of ones in that particular code word. And then just do it again. And then calculate the Hamming distance between those 2 code words corresponding to each of those messages. Then you're going to run through that last little example for each of these, right? Once you've done one, it should be plug and chug. And in fact, if you want, you can go over to lab and I think back in my day when I was teaching there full time, we had MATLAB on the computers and the RLC lab on the first floor over there. That was before the new engineering building was built, so I have no idea what things are like there now. But hopefully, you can get hold of MATLAB somewhere. This is a little messy, but you can create your G matrix, okay, and then you can peel off your parity matrix from that. You can create your HT for that. Well, you got to use the right syntax here, and then you're creating your H of T, and then you can take I just created a particular code word up here somewhere. Where I have my message, and I multiply that by G. So I have here the 1100. I'm multiplying that by G. I get 1100 systematic code, right? It's just replicated there, and I got 211. Well, you got to teach MATLAB how to do modulo 2 addition, so that you can just do mod, and then the first argument will be the expression that you have, and then comma 2 will make it modulo 2. So it'll take any 2s, and that'll be a 0, right? Through the modulo operation. 2 divided by 2, what's the remainder? The remainder is 0, right? So so that's just a little trick. So you can create a whole matrix of D's here. And let's see, let me just print out my D matrix, right? So this is message length of 4, K is equal to 4, every combination. I think I got that right? And G is this, so if we do mod D times G, comma 2, then we end up with this table of code words, right? So that might be an easy way of generating these things, and then you can actually do all your other equations with that, like this R times H of T, although again you might want to use the mod operator on that. So all right, any questions overall here? Okay, Monday seemed like a reasonable, next Tuesday before, class would be, reasonable for submitting that, I think. Okay, so I do plan on, heading to New York to see my family, after class on Friday. So, hopefully you'll, see me in lecture for a week and a half or so. So, all right, I guess we're done a little bit early. So, unless there's any other questions, I'll let you go, and we'll see you online on Friday.
Sounds good. Have a good one, Professor. Be well.
Thank you, Professor.
Mhm. So, did you